So this is the first of 4 videos about gases and gas laws. The reason there's only 4 videos is that gases are a topic we've been talking about a lot already with stoichiometry and reactions. You've seen gases in equilibrium, so there's not necessarily a lot of new things to add. The other good part about gases is probably 75 to 80% of the things you need to know about gases we covered in first year chemistry, and like I said, a lot of it we've already been reviewing. So several of these videos are going to be refreshers, just kind of practicing some things you already know, refreshing you on things you already know. But in each one we'll have a little bit of new stuff, maybe some things looking at gases slightly differently than before. So the reason gases get their own chapter is that all gases, whether it's noble gases or whether it's gases that are bonded together or the mixture of nitrogen and oxygen and CO2 in the air, they all have very similar physical properties. Not huge differences in densities, not huge differences in the way the particles act. So a lot of the explanations for gases are the same no matter what it is. There is some different chemical reactions, there is some differences in some of the properties, but for the most part there's more similarities than differences. So as we look at these models here, we've got a solid, we've got a liquid, we've got a gas. With solids and liquids, you see the particles are very close to one another. A lot of times people describe solids as the particles are very close, and then liquids, the particles kind of have a medium distance between them. But as you look at these and as you look at those, the particles are just as close. In fact, some of the liquid molecules are closer to one another than a few of the solids are, but the difference is in the degree of order. Solids are orderly and the molecules vibrate in place. Liquids are a little bit less orderly and free to move. So solids maintain their shape, solids maintain their volume, but because liquids are just as close together, they maintain their volume while being able to change shape or take the shape of the container. And here's a gas, and this may not even be the best description of the gas because there's still a lot of particles that are very close. In gases, the particles are very spread out. And because of that, they're able to take the shape and completely fill the volume of whatever container they're in. They will expand, but they can also be compressed. So we can put a gas into a small container, but if we put it into a big container, it will expand to fill that container. With liquids and with solutions, they only mix depending on the polarity, depending on the strengths of the attractions. But particles of gases, because they're not mixing by attractions to one another, they're mixing by random motion, they always mix. The only time that they wouldn't form a homogeneous mixture is if we have some sort of chemical reaction between the gases making a new compound. When we talk about these, and we'll see some of this later as we describe the particles themselves take up just a tiny, tiny bit of the total volume. A container that's full of gas is really mostly empty space. So when you're little and then you have some water in a cup and you pour it out and you ask your parents, well, what's in the cup now? And then they say it's empty, and then you say, no, it's full of air. That's true. That's when you're first learning about air and matter in your first science classes. But that air that's there, the nitrogen, the oxygen, the CO2, the distance between those particles is so huge compared to the size of the particles themselves that it really is mostly emptiness there. So these far apart molecules act as if the other particles aren't there. There's not very much interaction or attraction between them, which is why, although this shows some differences between these, really they should be even further apart completely to show it totally accurately. But I wanted to have a model that had a similar number of particles. So we kind of think of these, whether it's a individual atom or a molecule, as small hard spheres in constant motion. As we are looking at gases, the measurements that we can make for them are listed here. We can know how many particles there are, we can know how much space they're taking up, we can know the temperature and the pressure. And pressure is something unique to gases, or at least in its importance. And with volume, we look at it a little bit differently because it's not just, its volume can change, so it is important to know the size of our container. Whereas if we had a solid or a liquid, It would be a defined volume regardless of the container. With a gas, it's the size of the container. Temperature is important, and we'll see this later, that we define it in terms of the average kinetic energy of the particles, but for all gas calculations and equations, it must be in Kelvin. Hopefully you remember that from first year. Hopefully you remember that from the problems we've already seen, but that's very, very important. You're going to be given it in Celsius more often than not, in multiple choice and in free response. You have to change that to Kelvin. There's lots of ways we can measure pressure. We'll talk a little bit more about those. But if I know the amount, if I know the liters, if I know the temperature and the pressure, I can find some other things. One thing that's not listed here is you can find the mass. We can go grams to moles, moles to grams. We do that by using the molar mass. So those two things are related to one another. If I know mass and moles, I can find molar mass. If I know molar mass and mass, I can find moles. If I know whatever else, whatever I didn't say, molar mass and moles, I can find mass. We can find density by looking at mass and volume, and these are normally going to be in grams per liter, and the density is going to be very small, especially compared to liquids or solids. And if we know the average kinetic energy, we can use that to find the particle's speed. We've got two different symbols here that we'll talk about in a little bit, but the idea is just knowing how fast most of our particles are going. So pressure is the thing that is unique to gases or different in terms of the way gases experience it compared to other things. Pressure is defined as force per unit area. So we've got a couple different equations here. And in physics, the unit we use for force is newtons. Area can be in any distance squared. Very often it's meters squared. So the unit of Pascal is based upon the amount of force, or 1 newton of force, spread over 1 square meter. That's not very much at all. That's a very low amount of force spread over a very large area, so that's very little pressure. So normally we're going to have not just dozens or hundreds, we would have thousands and hundreds of thousands of pascals when we're talking about even air pressure here. And the reason they exert pressure, we've got some important things here, is the fact that the particles are moving. So pressure comes from force. And when those small hard spheres in constant motion are bouncing around, they bounce off of one another and they bounce off of the surface of whatever container they are in. So if I want to think about what's causing that pressure, it is the force of collisions. If I want more or less pressure, I have to change how many collisions there are, maybe changing how many particles there are. I have to change the frequency with which they collide, making it happen more or less often by getting the particles moving faster or slower. I have to change the force of those collisions. Are they bouncing off the container harder or softer? The other way I can change the number and frequency of collisions, keep the gas doing the same thing, but put it in a smaller container. So those were descriptions of how we can change it that all go back to this. If I change N, the number of moles, the number of particles, that would make either more or less collisions. If I change the volume, that would mean the particles run into it more often or less often. If I make the particles move faster, they will run into them more often or less often, or I guess faster would be more often. Slower would be less often, and they will have either more or less force. So these are the variables that can change the pressure. And when we're discussing this or looking at this, we measure pressure with the barometer. And now we use barometers that are normally digital. They have a pressure sensor measuring force over that defined area, but you'll definitely still see questions asking about barometers, kind of the classic mercury barometer. So in a mercury barometer, you have a tube that you fill totally full of mercury, and then you turn it over into a pool of mercury. And when I say you fill it totally full, that may not make sense with this picture because it doesn't look totally full. But what happens when you turn it over, gravity pulls that mercury down. And because mercury is dense, it pulls it down pretty well because of the large amount of mass. But the opposing force to that is the air pressure, the atmospheric pressure that's pushing on this pool of mercury. So we've got two forces. We've got the force of the air, all of those particles that are colliding and bouncing on the mercury, but then we've got gravity pulling the weight, or causing the weight of mercury, pulling it downward. So at a certain point, those two forces are equal and opposite, and the mercury stops moving. That is where and how we measure the pressure. We see, okay, right there, that's the mercury level. So that's how much pressure we have on that given day. If the air pressure goes up, then there's more pushing here. That would cause it to go even higher. When the air pressure goes down, we would have less force and fewer collisions on it, so then this could fall further down because there's not as much forcing it upwards. So we've got this push, which then forces the mercury up and in. When that decreases, we have less pushing it upwards and inwards. So this 760, we'll see, it's right down here, is standard pressure. On a normal pressure day at sea level, the force and pressure from the air pushes mercury up to a height of 760 millimeters of mercury. So I mentioned gravity a few times, and I mentioned sea level there. Gas particles have mass. That means they are affected by the gravitational force of the Earth. So just like anything, they should be pulled down to the surface of the Earth. But because they have kinetic energy, because their mass is fairly small, relatively speaking, it doesn't take much energy to overcome that attraction to a certain degree. So gas particles aren't all just on the very surface of the Earth. They're moving around, but there is a much higher density, a much higher concentration close to the surface of the Earth. So at sea level, or at the surface of the Earth, we have a very high pressure, or the higher pressure. On a standard pressure day, the pressure we define as 1 atmosphere, which, as I said, is equal to 760 millimeters of mercury. Because it's not always measured with mercury anymore, there's some other units that are sometimes used, and an equivalent unit to millimeters of mercury is torr. So 760 torr, 760 millimeters of mercury, 1 atmosphere, those are all different ways of saying standard pressure. And those are all given on the equation sheet with your periodic table. These other ones, 14.7 psi, that's a very common unit. We use psi when you're looking at your tire pressure, when you're looking at your maybe inflating a basketball or a football. The psi stands for pounds, which is a unit of force, per square inch, which is a unit of area. Bar and kilopascals are just other units. You may see them, but they're not ones that you need to know these values off the top of your head. So then we have here, as I said, pressure is affected by the gravity, so at a higher elevation, we have fewer particles. So if you go to the top of a mountain, you're going to feel a difference in, a lot of times it's described, the thinness of the air. The air seems thinner because there's fewer air particles per unit volume there. They're still expanding and spreading out. There's just not as many of them there. So each time you breathe in and out, instead of having that same amount of oxygen, you're going to get fewer oxygen particles each time you breathe. So here a barometer measures the pressure of the air or the atmosphere, and we have a different tool that measures when we have an enclosed gas. That's called a manometer, a manometer, but it's pronounced manometer. It exerts pressure inside a container. So here we have some gases inside a container. We could also just use, pressure sensor, measure the force per unit area, but this is very common to see this diagram on multiple choice. So you've got diagrams here we'll practice with, but here we've got just some very common simple pictures to look at this. So whenever you're looking at, whether it's a barometer or specifically a manometer, you're looking at which side is pushing harder. Up here we have no gas particles, that's what a vacuum means. Here we have some gas that's pushing. So we have no pressure over here, we have some pressure here, and that's what's causing, instead of the mercury levels to be equal, the mercury to scoot this direction and be higher on that side. Some books and some teachers kind of focus on, okay, memorize whichever's this minus this or that minus that there's a specific equation for these. But you really just want to look at which side is pushing harder and how much higher is the mercury level. If these were equal in pressure, and I don't have a drawing like that, we would see, okay, maybe the two levels would be equal. Cross all of that out. I know this isn't very clear, but if those two are equal, the pressure inside and outside is the same, and that's what the next one has, so I don't know why I just drew all of that. So this next one, we have two levels that are equal. That means the pressure here is equal to the pressure there. So this is open over here. It's very important to read these. This is a vacuum. We see this one's open, so we have a certain force coming in there, or a certain force per unit area, which is pressure, certain force per unit area of pressure here. So the pressure here and the pressure there are the same, which is why the pressures are equal, or why we know this is 1 atmosphere inside. Here we have an open container again. We have some pressure on this side, we have some pressure on this side, but now instead of being equal, the mercury has shifted around. This side is higher, so that means this is a large pressure, this is a small pressure, and the difference in pressure is defined by the difference in height, 760 millimeters in this case. So if the atmosphere was 760, this would be double that, 1520. So we have a few conversions here, just very simple math. We'll do those pretty quickly. These are all things you need to be able to do. So the first one here, 25.5 Celsius, changing that to Kelvin. You need to know this, but this is an equation on the periodic table, so I'll write them over here. That it says Kelvin equals Celsius plus 273. So this is very simple. 25.5 plus 273, that's going to be 298.5 Kelvin. Whenever you do any calculation involving temperature as it relates to gases, you need to change that to Kelvin. Another thing that you will be given, and let me clean these things up, another thing that you'll be given is the relationships for the pressure. So I said 1 atmosphere is equal to 760 torr, which is 760 millimeters of mercury. You are given that, and depending what value of R you are using, which we'll talk about in a little bit, depending exactly what you're solving for, you may need to convert between millimeters of mercury and atmospheres. When you do that, in this problem right here, you see 745. You should be able to estimate, especially for multiple choice, okay, my pressure's right around 1 atmosphere, but slightly less. But for the actual calculation, let's do this. We would say we have 745, that should be there's the 745.2, and then we do that at 1 atmosphere for 760 millimeters of mercury. The answer on this comes out to 0.9805. That is how many atmospheres you have. So a little bit less than 1, just as I said. The last thing here is make sure you know how to get from milliliters to liters, liters to milliliters. That's definitely an important or vital thing to be able to do. The conversion between kilo and milli are definitely expected. So we've got milliliters. A milliliter is a small amount, and this is a small amount of milliliters to begin with. To get that to liters, we are moving the decimal 3 places. So I've got 9.43 times 10 to the negative second. That's going to be 9.43 times 10 to the negative 5th liters. Make sure you know which one is bigger. Make sure you take an extra second to make sure that your answer makes sense. You're moving the decimal 3 places, but a liter is a much larger amount than a milliliter, so we have far fewer liters than we do milliliters. And then we have some manometer problems here to wrap this first video up. Calculate the pressure of the enclosed gas in each instance. So here we have a small push there and a large push there. It tells us what this value is. So that is 755. tells us the height, the difference between those. So this one is more. So it's going to be 755, but since the inside is pushing more than the outside, we would add 24. We would have 779, either torr or millimeters of mercury, both are equivalent measurements, as our pressure of the enclosed gas. So once again, if you look to another source, you may see an equation. I don't even know exactly how the equation's written because it comes down to memorizing things that I don't think make sense to memorize, or really memorizing multiple equations. So you're looking which side is pushing harder, inside or outside. The inside's pushing harder, so its pressure is higher. In the second one, we've got a small push inside, we've got a big push outside. So 763 from the outside, well, the inside is 35 less than that. So the inside 728 millimeters of mercury. This definitely could be multiple choice, and you'll see it on multiple choice, but it's also a really good question to sneak in as part of a free response, just to make sure you understand the pressure of your enclosed gas. A lot of times you would be told, okay, a reaction happens in an evacuated vessel. So you got a vessel with no pressure. Then as the gas is being produced, the pressure increases. It could say it's connected to a manometer, which is open to the atmosphere. The mercury level inside is this much more or less than outside. So instead of giving you directly the pressure of your gas, asking to make sure that you understand the concept of pressure and understand atmospheric pressure. So don't be surprised to see that multiple choice or free response. So those are the basics of gases and hopefully mostly a review. The next video is going to be about starting with the calculations, the gas laws, and hopefully you remember those pretty well.